Thank you, everyone. I'm PhD student at Politecnico, Bari, and I'm going to present my topic, highly sensitive Mach-Zehnder Interferometer, glucose biosensor with sub-wavelength grating inflexible substrate. Outline of my presentation is a bit about diabetes trends, background and motivation, the proposed sensor design, results and discussion, finally state-of-art comparison and the conclusion. These are about some facts and figures about the diabetes. Diabetes is a chronic illness which is affecting millions of people globally. According to IDF, International Diabetes Federation report, and there are about 537 million people around the globe, which is in 2021, and these figures are about to reach around 643 and 783 millions in 2030 and 2045 years. And also in 2021, people's age between 20 to 79 years, they died because of diabetes. This is a figure which is showing the overall worldwide increase of this disease. And according to European highlights, 1 in 11 adults have diabetes, and by increasing our increased rate of 13%, there will be around 69 million people with diabetes in 2045. And average cost per person is around $3,000. A bit about research background. There are a number of efforts like optical sensors, electrochemical sensors, and fiber sensor, but they have several limitations. Like they are used for laboratory setups only. They are bulky in nature. They have light penetration issues into the skins, enzymatic reaction time, and activity to generate sweat, and also how some extraction mechanism are used just to extract the interstitial fluid for glucose sensing. Also the commercial glucose sensors, there are a lot of commercial glucose sensors, like one is Dexcom G6, which is currently used commercially for glucose sensing. But they have the problems, like they have to be inserted beneath the skins, and you have to replace after like maximum time of 14 days. And after that, they need to be replaced, which is a painful task. Also, they have the limitation like you need to calibrate the sensors again by finger pricking method. In order to overcome these limitation and a non-invasive way to glucose sensing, there is a need of a sensor which should be a wearable, flexible, biocompatible, and user-friendly. So why photonic sensor? Because photonic sensors is high sensitivity. They have fast response time, compact in size, low sample volume, and they are more flexible. Therefore, we proposed a proof of concept just to measure the glucose by using a subwavelength grating structure over a flexible substrate. This is the concentration of glucose in different biofluids, majorly in blood. And in comparison with blood, there are other biofluids which are interstitial fluids, saliva, tears, and sweat. Since we are targeting sports application, so we are using sweat as a biomolecule just to analyze the glucose level. And because there are extraction mechanisms which are used for blood and ISF, so sweat is a perfect alternative just to analyze the glucose level in a non-invasive way. Actually, the problem with detecting the diabetes is the non-invasiveness. If every patient has to like prick his finger, which is like tedious and painful task with the passage of time for me. So there must be some convenient way just to monitor the glucose level. This is the overall layer structure of the proposed sensor, in which I selected PDMS as a substrate material. Why PDMS? Because it's thermally stable, it's flexible, and it's elastic nature while bending. And silicon as a core material for waveguide geometry. There is glucose. We are using glucose oxidase. It's the enzyme layer, which is specifically targeting the glucose molecules only. And finally, the hydrogel patch, so we can collect the sweat so that it can interact with the main sensing part of the device. This is the proposed sensor design. I'm using MZI, Mach-Zehnder Interferometer, in sub-wavelength grating, and The figure is showing the subwavelength grating structure, and figure B and C are the cross-sectional view for sensing arm and the reference arm. The core for the core width, the width of the core is 450 nanometer and height is to 20 nanometer, and the thickness of GX layer is 500 nanometer, so that it should be greater than the penetration depth of the sensing media. In basic working of Mach-Zehnder Interferometer, light from a laser source is directed through 3 dB MMI input coupler. So it splits into two arms. One is sensing arm. In sensing arm is like where the light interact with target analytes, and other one is the reference arm, which is covered with some non-sensing media. We covered it with flexible material like PDMS. At the output, there are again 3 dB MMI power combiner, which combine the separated lights, and a spectrogram just to show the output spectra of the measurement. How the wavelength shift is measured with change of glucose concentration with the sensing arm and the reference arm. Here is some novel feature of the proposed structure: higher glucose sensitivity, because the part of core mode, in addition to the emanation field, is also interacting with the sensing media. Selectivity, because we are using glucose oxidase enzyme layer just to ensure the specificity to glucose molecules only. Structure flexibility. Structure flexibility is most important because we are targeting some sports application. So body parts move. So instead of using a rigid core, we use silicon in SWG, subwavelength grating arrangement, to make the structure more flexible. And stability against the external parameter in MZI configuration, there is a shift in resonance wavelength, which is compared in sensing arm with respect to the reference arm. So since we are using silicon for both arms of the MZI, therefore the parameter effects which are affecting externally should be very small and provide more stability. Here is the transmission spectra, which I plotted for a conventional MZI, in which there is like no subwavelength grating, and the conventional, and the other one is subwavelength grating structure. For the glucose concentration change from 0 to 1.5 milligram milliliter. So in large view, for a conventional MZI, shift in resonance wavelength is very small as compared to the SWG for the similar change of glucose concentration from 0 to 1.5. Here is the sensitivity comparison for conventional and SWG MZI. For conventional, it is 0.2 nanometer, and for SWG, it's 4.1. It is around more than 20 times sensitivity enhancement in our proposed structure as compared to the conventional. The graph is showing the sensitivity comparison for conventional and SWG MZI. This is the state-of-art comparison, and in this comparison is about the sensitivity analysis reported in the literature and with our work, which clearly shows the sensitivity enhancement as 20 times more than reported in the literatures. Finally, the conclusion, like we target a novel design of MZI with a concentration range of 0 to 1.5 mgml, higher sensitivity value of 4.1, which is 20 times more than the conventional MZI. The proposed structure is more flexible, high sensitivity value, high selectivity, flexibility against external parameters. So this unique MZI design may open some possibilities to measure the glucose in a non-invasive and convenient way, and it's a technology or the effort for the advancement in sensing technology in future. That's all. Thank you.